Welcome back. This is F#Conf, still alive from Channel 9, and I already have our next speaker with us, Gina. So Gina, where are you based? I see there's still a little bit of sun outside.
Hi. Yes, I'm based in Jersey City, New Jersey, and it's bright and sunny right now, even though we had flooding earlier today.
Oh,
So yeah,
I was just
happy for the sunshine.
that's all right. I was just chatting with Vincent, who's doing the next talk, and he had a false fire alarm. So maybe we'll have some fire, some flood. I think the last thing we're missing is an earthquake.
Yeah, this talk is turning out to be epic biblical proportions.
It's earth-shattering, literally. All right. So you're going to be talking about distributed tracing. Is this something based on your work? Because I know you've been working at Jet.
Yes, I'll go ahead and get right into the talk, and I'll go ahead and switch over to my slides.
Sounds good. Let's do that, and then I'll come back for the Q&A at the end, and we'll switch to the slides, and I'll turn off my video as well, and you're live. Thank you.
Okay, awesome. Okay, yeah, so this talk is about distributed tracing at Jet, some of the lessons that we learned, hard-fought lessons. So this is sort of an in-the-trenches view of what worked, what didn't when we were building our tracing libraries in F#. All right, so let's get into it. So I work for Jet.com, and for those who don't know, Jet is an e-commerce company that serves the American public. So for those who are not in America, they may not have used Jet before. Jet is, when I say e-commerce is just a fancy word that means, an online store where you can buy things. So you can buy cat litter on Jet, you can buy toilet paper, anything your heart desires, you can buy it on Jet. So this is me. I'm Gina Maini. My last name rhymes with linguini, so easy to remember that. And if you have any questions after this talk, feel free to at me on Twitter and ask me any questions, or go ahead and directly message me. These are some really important contributors to our distributed tracing libraries. Although there's not everybody up there, I'm also missing a set who's on my team. So I should update this slide post talk. But these are some really important people who worked on these libraries with me, and definitely could not have done this talk without them. So a little bit more about Jet. So when we start to talk about distributed tracing, we also need to understand what is the basic architecture at Jet.com, what types of problem spaces does Jet deal with. So our architecture is a bit niche and interesting for an e-commerce company. We do something called event sourcing. So event sourcing is basically, in a given system, your source of truth is an event. Now, this is sort of different than a traditional architecture in the sense that maybe in a traditional company, you might be sort of joining on tables to create a unique entity. But at Jet.com, all events are immutable, and we sort of compute state based on crunching a stream of events. So we also use F# at Jet, and that shouldn't surprise anyone, given that this is the F# conference. More on that later. Jet also runs multi-region. This is kind of cool. It's very cool, actually. And basically, we run failovers pretty much every week. So we run in, 2 different regions, many regions, and we'll continue to add more as we grow. Jet uses containerized deployment mechanisms. So you write a service and you sort of deploy it in a container, which comes with all sorts of nice accoutrement, like service discovery, secret keeping. We use Nomad for that. Jet is also fundamentally asynchronous, and this is actually a really important point to the rest of the talk, given that most of our what we call tier 2 and tier 3 services are asynchronous. And I'll dig into what tiers mean at Jet, but basically tier 1 is sort of our high level user interactions that might be happening over HTTP, where if you check out on Jet.com, that anything that touches that might be tier 1. But sort of our auxiliary inventory processing and maybe our ETL jobs, those might be tier 2 and tier 3. So if they go down, we can handle a bit of a delay there. So asynchronous, meaning that we might write our events, remember I said we were event sourced, to a bus asynchronously, and later we might have our downstream services read from that bus asynchronously. So it's kind of hard to guarantee the order in which these actions can happen, because really we don't want to think about order. We just want to have an asynchronous write and an asynchronous read. So we're also hosted in Azure. Sometimes when I talk about Jet at other places, people are sort of surprised that we don't use AWS, but I think it's pretty obvious. We're in competition with Amazon, and we use a .NET stack. And I work on the Marvel team. So at Jet, we have superheroes which map to basically every team, which it's kind of silly, but anyway, Marvel is the core platform and library team. So we're releasing new libraries every 2 weeks to the rest of Jet engineering. So why does Jet care about distributed tracing? I think that's a really important question before we begin, because it kind of puts what is distributed tracing and how does it pertain to Jet in focus. So here's the type of a query that we may want to know about at jet.com. So show me all inventory updates which failed for a given merchant. So if we unpack what that query is asking there, it's talking about an inventory update, which we don't really know what that is yet, but presumably some sort of action. And this action can apparently succeed and it can apparently fail. And it seems like we're also trying to group by or join by a merchant. So what do I mean when I say merchant? It sort of sounds like, Civilization 5, like the merchant, like non-playable. But that's not what I'm talking about. When I say merchant, I mean a third-party vendor like Nike or Apple, who may want to go into our user interface for our vendors and update the price of a SKU. A SKU here is just a unique identifier for any item. So Nike wants to go on the site, change the price of a sneaker, and voila, you have the new price. But, this is kind of a complicated thing when you really start to get into it, because an inventory update, we don't really know what that is, and we don't really know how many systems are involved in an inventory update. So kind of hard to go about determining what, an SLA or a success or a failure would be for an inventory update. Okay, so maybe if you were trying to solve this query, you might first start with, okay, what's an inventory update? So you might go to the inventory team and say, hey, can you draw me a diagram of everything that's going on in an inventory update? And they might give you something that looks a little like this. So our merchant here, which is the user in this slide, might go into their dashboard and they might change the price of a SKU, and that's all going to be happening synchronously. So that's a very typical request, reply, response, which requires an acknowledgement over HTTP. So they're going to update, and that's going to talk to a merchant API, which is just going to be an HTTP server. Now this server may queue something. It may add this update to some sort of inventory bus, which then publishes to a catalog. We don't exactly know what this catalog is, but maybe downstream this catalog adds that update to some sort of re-indexing topic, to a search topic maybe, which later gets published to Elasticsearch. Okay, so all of these interactions here basically comprise updating a SKU. So you change, the merchant logs on, changes a SKU, it publishes asynchronously to a few different topics in Kafka maybe, and downstream some Elasticsearch index is updated with the new price. Okay, fairly straightforward, but remember, failure and success is what we're talking about here. So let's say, for example, that Kafka goes down, right? The brokers are borked or the topic's the wrong name, some catastrophe happens, and it's kind of hard to determine, well, did it go wrong in the HTTP layer? Did it go wrong in the Elasticsearch layer? When you start to go through this call graph of actions, it can be hard to determine causality, because remember, this is a distributed system where all of these updates are happening asynchronously for the most part. So it can be hard to determine what happened when. So that's really what we're trying to do here. So I could take that same flow and I could split it up in a visualization that looks something like this. So here I've drawn lines. These dotted lines kind of represent different domains, different system domains. So we've got this sort of synchronous update for updating a SKU, which sort of enqueues and then dequeues asynchronously into some indexing layer, which then publishes to Elasticsearch. So what you've seen that I've done here is you've noticed that I've color-coded my arrows in 2 different colors. So my yellow here is representing an HTTP interaction, which is sort of request reply, meaning that if I wanted to take an SLA or a service level agreement on it, I could say, okay, well, this should only take under, 1,000 milliseconds or 500 milliseconds is my SLA. Let's say that would be quite peppy, but let's say it's that. And then, but determining an SLA around these asynchronous actions, they might be kind of different, right? Because my objective here is not really to have a time frame in which it happens, but have the ability to publish at will, right? So I've got these 2 different types of communication styles I'm trying to model here, so I've color-coded them differently. We can also kind of look at this as a series of events, right? Because remember, JET is event source, so that kind of sounds like our type of semantic. So in the synchronous interaction, we've got our start and complete for each span. So the user initiates an action, which initiates another sub-action within the merchant API, right? And those have their definitive completes. And then we also kind of have these asynchronous start and completes. And maybe I've added in the bottom there when we're publishing to Elasticsearch and some sort of custom info event, right? Let's just say, because remember, this is just a series of events around communications. So we can kind of talk about these communications regardless of the style they are based on their start and complete. So we could also look at this like a time log. So here I've drawn time as continuing, and we have a series of events that happen. This looks very similar to what we expect in an event source system. And remember, because of these asynchronous events, a complete may come into our log before a start, or vice versa when it wouldn't be appropriate. So timestamp here, especially in a distributed system, can be unreliable, particularly because each of these machines, presumably they're operating on different machines, but of course they could be operating on the same machine, have different clocks. So really getting a time-ordered log is a bit tricky, but basically this is kind of what it looks like. So, okay, we've talked a little bit about what types of communications we want to trace and how that might look. So how could we solve this problem today, right? Like what exists that JET could use? So this slide has an overview of a couple different important players in this space. I also should add OpenZipkin to this slide as well. But basically, these are the major players. OpenTracing is an important one. A lot of people are moving to standardize based on OpenTracing, which is essentially, sort of, as it says on the slide, a vendor-neutral open standard, meaning it gives some structured semantics to OpenTracing, but the problem with that is it had very limited description on how asynchronous interactions would work. And remember, JET's Tier 2 and Tier 3 are really all asynchronous. And it thusly follows that Dapper and Zipkin and others really specialize in sort of a time series view of RPC-based spans, RPC being request-reply interactions. So a span or a latency on how long it takes to write to Kafka may not be the actual thing that a developer wants to know. They might have other ways of calculating those SLAs. What they want to know is that it completed. That's really what they want to know. So none of these tools really encompassed for us a total complete package of how we were going to do this in our system. So we sort of decided to build our own. So we decided to make our own. What could go wrong? Well, turns out a lot of things went very wrong. I think it got very tricky. And I'm going to talk about basically each of these different problems that we encountered when we tried to solve user needs with our tracing libraries. And we're going to talk about some of the lessons learned there. But, you may be wondering like, well, okay, if you guys didn't really win at this, why are you even giving a talk about this? And I guess my answer to that would be, I've basically like failed a lot in my career, and I'm not here to tell you how to do it at your company perfectly. That's something that you're going to have to decide for yourself with your team. But, my mistakes will become your successes. And that's really what this talk is about. I want you to take away, how might I practically add some interesting ways to trace my flows, and what kind of considerations should I make when I try to trace them? Okay, so what was here's a first problem we encountered. So we tried to trace everything at once. And, the problem with this is, in distributed tracing, it's easy to think that, oh, well, if I trace everything, then the value of my product goes up, right? Which makes sense, because, to trace things, you need to kind of instrument multiple systems to have a valuable product, right? Makes sense. But we sort of treated this more like an R&D project, and sort of built these things in ivory towers. So when we actually started to kind of like instrument these multiple services, we met with a lot of different resistance, because it provided a lot of overhead for different teams. What we should have done was treat this like a traditional product, where we kind of carve out, okay, what's the MVP on the trace that we want to do, and how do we successfully deliver that for these individual teams? So, that's kind of more of a commentary on how to build successful software. But, I think it's particularly painful in tracing. When I travel around and I talk to other people at other companies like Facebook and Netflix, and, I ask about their distributed tracing, it usually ends up being like one guy who built a dashboard, and it's a really nice dashboard. But when I ask, like, are people using this to solve real problems in production, the story gets a bit hazy, right? No one's really using it or sponsoring that product. So, this is more of a shout out to people trying to do cross-team projects, but really make sure you can identify sponsors and people who are going to want to use your tool, and work with them, because, these types of tracing libraries can be really difficult to instrument in all of these different communication layers. So find people who want to see this succeed, who have a problem they're trying to solve, and really focus to meet that need. The other problem we had was, we sort of developed this unwieldy over-the-wire specification. And I'll show you some examples of what those types look like and what I mean by unwieldy. But basically, in distributed tracing and in OpenTracing, there's this concept called baggage, which is a great actual word for it, because you're sort of carrying this baggage as you propagate a trace. And we'll get into what propagation is in a moment, but baggage is essentially just key value pairs that scope across the whole trace. So remember that query I asked about a merchant for a given merchant. Well, in this case, baggage would be like maybe merchant ID and then the ID number, right? So it's a key value pair that gets propagated as these events are happening within your service. Okay, so how did we solve these problems with our over-the-wire specification? We essentially scaled back the amount of data that we were telling people to copy in the headers. In the beginning, we also tried to bolt on schematization at Jet. And, that sort of makes sense, because if you think about services as a topology, services are communicating where their edges are schemas. So we sort of thought, okay, we'll also allow a schema field in the header, and no problem. But the problem was, there weren't structured schemas at Jet, and people didn't really know who owned which schema. So when I say schema here, I just mean the structure of, in our case, the JSON where events were emitting. So no one was really versioning them. It was not really a lot of ownership around which schema belonged where. So really hard for people to parse out what they should even be putting in these headers. And so we really scaled it back and just had a wire spec that contained unique identifiers, GUIDs, and operation names, right? That's really it. So you may not know about the entire trace, but you will know about the name of your operation, like merchant API or catalog update. And all of the rest of these key value pairs, we did sort of put them in the header still, but we just emitted them as events. So really only the baggage that pertained to the entire trace was carried. Everything else, like let's say IP address or machine name, service name, those types of things, those were just scoped to the events themselves, and we took them out of the header. So really important change there. So here's an example of our old metadata format. We have a record type here, type header, and it's got a lot of stuff in it. And immediately off the bat, you know it stinks because it's Pascal case. No, I'm just joking. That's a very bad joke. But it's not cool because, you know, you've got payload schema URI here. Remember I mentioned schemas, and it's kind of like, well, what does that mean? You know, presumably there's some schema URI. And, you know, when developers looked at this, they were like, wait, is that the same thing as my controller path in my HTTP server? And we were like, no, it's, you know, the schema. We also had a timestamp called ticks from epoch. Very confusing. I don't know why we didn't just call it timestamp. And then we delineated these tags based on were they scoped to the whole trace, like a merchant ID, or were they just relevant to one hop or span in that trace, like IP address or machine name. But really, we just emitted those ephemeral types of key values in events, and we took it out of the header because it just provided both. We also took out the need for you to understand parent ID or message ID. That became internal. And basically what that was a linked list of GUIDs that represented, you know, who did what where. Producer ID also went away. We just had an operation name now. Producer ID was very complicated for people to understand. Was it the people who were creating the trace? Was it the individual service? So there was a lot of confusion around that. This is what we got to. So new type, trace context, which kind of lives ambiently in your service, that has a trace ID, which is a GUID, but here we just kept it a string for simplicity. It had an op name, and it had some tags. Now, we had, we had our own secret sauce tags that we were formatting inside of here, but essentially that's really it. That was the only thing going over the wire, and it kept things a lot simpler. So another problem that we had was the library wasn't great. And what I mean by not great was, you know, it required a lot of overhead. We basically, in the V1 library, added very low-level functionality where you had to know about the entire trace. You had to know, you know, you had to know quite a bit. It was a lot of overhead, and we did provide a lot of documentation, but the funny thing about documentation is developers are busy, and they're probably not going to read it. So you really need to create auto-magical out-of-box tracing. And we didn't do that first. We started too low level, and it really confused people. Also in the beginning, we tried to use thread local storage to store some of these trace contexts. But that also proved very difficult to reason about, and a lot of bugs emerged, a lot of overhead for developers. So where we got to is sort of auto-calculating span latencies, which is, you know, end-to-end SLA of a trace is really what people want to know. So we just went ahead and auto did that for you. We integrated with Nomad metadata. This is sort of still an experimentation, but basically we decorated these ephemeral tags with all of the container information that you ship your service with. We also utilize computation expressions in F# to sort of have an ambient context which lived inside of your async builder. So you could summon this context and inside of it be able to send to a tracing log and, you know, get information from that tracing log. So that's how we started to do more of a high-level semantic around tracing. We also decided to have, instead of having an enveloping type, which I'll show you an example of what I mean by that, but basically a type where it's a tuple of a header and a payload, we decided to think about it more medium-based. So instead of having people rewrite their code to be completely envelope-aware, we sort of had them rewrite their code to be Kafka-aware or integrate with our event streaming libraries. So and HTTP. So we wanted to have out-of-box ways to work over these mediums, but because we figured that's easier for the developer to understand is how can I write something to a Kafka bus? How can I have an HTTP server that automatically does tracing? So that's what we focused on. And this was actually a good thing that we did from the beginning, but basically when services emitted these communication events like start, complete, they did so asynchronously. And in memory, these kind of got aggregated to a file, which then this file was watched by a daemon, and those individual events went straight to our Kafka topic. So what was great about that was people didn't have to manage, you know, a Kafka producer. They didn't even have to know about Kafka. And if the thing went down, no big deal, right? The daemon just sort of forks, and their service runs as normal, which was really important for us. We wanted to keep sort of a tier 3 quality about our tracing library. It should not impact your fundamental uptime. But actually, what was funny about the busing of the events is actually services lost their CPU went up quite a bit simply because of the JSON serialization to that file. So in subsequent versions of the library, we really had to optimize JSON, which, you know, hand rolling JSON, just like Mama used to make, you know, it's ugly work, but it really optimized for fast output, which we wanted. So here's an example of some propagation. Remember I said that word earlier. So here we have a microservice kind of represented with that funny letter in the middle. And this is kind of how we can think about how inputs and outputs work inside of a microservice. So we kind of have this over-the-wire input, which contains some trace information in the header, and it's got a payload of some, you know, event format or maybe an action request, some schematized data that they're going to read and deserialize. So once they take this over-the-wire input, they're going to deserialize the header and the payload, and suddenly inside of this service, propagation happens, which transforms the header. So what happens during propagation? We continue the trace ID, we copy that trace over, which links these communications together in a call graph, and then we decorate it with a new GUID that represents the running operation. We carry over maybe some metadata, some key value pairs like merchant that they wanted to keep throughout the trace, and then they kind of serialize that to their over-the-wire output. Now, if you look at this, there's discrete states here, right? There's probably 5 states that we need to represent in the library. And you might be thinking, you know, I had someone come up to me after I gave this talk in London, and they said, well, aren't you overthinking this? Like, why do people even need to know anything about this? And, you know, he's totally right. We definitely overthink things a lot at JET, but I would say, you know, we needed to think about these discrete states specifically for the people who wanted the low-level functionality, who wanted to add merchant ID, who wanted to decorate traces with useful information for their own alerting. So we kind of had to represent these states because it wouldn't really make sense to propagate something that had, for example, already been propagated, or it wouldn't make sense to try to copy data from a serialized message. So we really had to represent them differently. So how did we do that in the first library? Well, we kind of defined these envelope types, right? So we had a type for serialized, in process, and out. Looks pretty straightforward. I think we can go back to that previous slide and make sense of what this might do. And we sort of use them in phantom types, which I'll get into what phantom types are. Phantom types are a neat, cool type system way to represent invalid states. So for example, you might have 2 types that are actually the same, let's say 2 floats or 2 doubles maybe, and each of these doubles, one might represent miles and one might represent kilometers. So even though they're both, you know, floats, you might not be able to add them together because that would be invalid, right? It doesn't make sense to add miles and add kilometers, right? They're different. So how you might go about doing that is representing it with a phantom type. So for example, we created functions for propagation where you explicitly passed a service name, a schema, the envelope that you wanted to decorate on the way out, and it gave you an out envelope, right? And you could not propagate, you know, an out envelope, or there were certain functionalities that you could not do, like mapping over an envelope if it was an out envelope. So basically very straightforward there, but we're just representing states as valid or invalid and preparing an out envelope type. But the problem with this is it got really crazy, right? Like all of a sudden you had to rewrite your entire code just to move over a payload in envelopes, you know, and it just got to be too much overhead for developers. Like, was this an in? Was it an in process? Like, what am I even doing? Like, what's the right thing to do? I just don't understand what I'm supposed to do. So that was kind of the problem that we had, was you had to rewrite all of your code in the envelope where not fun to rewrite your code, and you just had to know too much about the low-level details of how propagation works. Not fun. So when we worked for kind of mediums,
we sort of had an encoding and decoding schema where, you would have an input and an output type and kind of what your payload might be for each of those and what it became in a trace context. So you would wire up these types for both like publishing to Kafka, maybe you have an HTTP server, and you kind of then didn't have to think about this encoding and decoding step. And we actually obfuscated a lot of these types through coding functions. You didn't even have to really be aware of these codecs at all. So that's kind of how we reworked it and hid it underneath the rest of our library. Okay. Okay, so now let's get into some of the experimental stuff we're doing, which is pretty cool stuff, I must say. And let's go to an editor. Hold on, let me go. Okay, here we go. Now, Thomas, can you see my my screen here? Oh, great. Just want to make sure that we traveled there. So here's an example script of how someone might use our, remember I said computation expressions in F#, and this is kind of advanced here, but oh no, you're supposed to see my editor. Well,
close the slides.
Yeah, let me try just closing the slides.
I can still see your slides.
Let me try. Yeah, I'm just gonna quit PowerPoint.
Yeah, because PowerPoint does crazy things to your machine.
Yeah, can you see now?
Still see the slides.
Huh, even though I quit. There might be a bit of a delay.
I can try just turning off the call and calling back again.
Yeah, that sounds good. Let's try that.
All right, I'll try that then.
Okay, we're back here.
All right,
so let me try sharing screen.
Yeah.
Okay. All right, can you see my editor now?
I see your editor now, perfect.
Awesome, thank you so much.
Experimental Xray ambient op.
Yes, doesn't this look exciting? This just tells the compiler not to warn about experimental code, but anyway, that's neither here nor there. These error codes are so interesting, but that's a topic for another talk. So anyway, this is an example script of how a service might use our what we call async omega, which is just a way to wrap up an async computation expression to basically do tracing for you. And what I mean by that is you're able to get an Xray context within this async omega. So you write a handler which communicates over async omega. You're able to do your request reply inside of this code, and then it's very straightforward in terms of writing an HTTP server. But here's the magic. So you basically are using this async omega builder in here, and let's kind of look at how we define that builder. So first of all, to define our builder, we kind of have to talk about a context that we're putting things in. So we define this as this async omega context, which basically has some put and get. It's pretty straightforward, just a concurrent dictionary here of key value pairs within this context. And then we basically ghost out all of the async function calls. So you can see here, we kind of have ways to get the context, put things in the context, remove things from the context, and we sort of define transactions over this context where you're able to grab this context inside of a transaction and run a function within that transaction. So here we make our little builder and we kind of ghost out all of these async calls, right? We redefine our bind, we redefine, lift and delay, things like that. And then, okay, here we go. We define our builder, pretty straightforward. And then if we go back to example code here, we're basically able to do things like have, in this example, we have, service A and service B, and service A is calling B as part of its trace.
remember that merchant API update, which had kind of a subspan within it. So maybe like an HTTP server, which calls an HTTP client. And this is kind of how you would do that. You'd create an Xray log in your service A. You would define a handler, which talked about the log. And then we have some work loading functions to instrument your HTTP client. Remember, I talked about that codec kind of working over channels. So boom, you get an instrumented client here. And now when you call both of these, maybe you host them, and here you're able to run them in parallel. Now that might be one thing that you want to do. So now let's open up our dist, tracing slides again. Let's go back. Hopefully this will work. PowerPoint.
We're still on editor. Still on editor. No, something's moving.
Okay.
Yeah, I think we will see your slide soon.
Okay.
Yeah, back on slides.
Back. All right, now we're going to speed through here. So this might update. Might be a bit of delay here. I love it when it's live. Okay, can you see the little imp?
Yes, feeling experimental.
Yeah, great. Okay, so thanks for sticking with me during that editor business. Now let's get back to talking about the event types in our system. And by the way, I don't think I said this, but the name of our tracing system is Xray, which you saw in that code when you wanted to generate a logger for tracing, you had an Xray log. I probably should have said that sooner, but basically our tracing system is named Xray. So we have a telemetry event type here, which again has the trace ID. That's the running GUID that represents the entire action here. We have an event type. Remember, our event types are start, complete. And we also had that info event we wanted to talk about, remember, in that ordered log. So in that case, we wanted people to be able to decorate tracing events and make their own tracing events. That's something that we added later on in our library. We have a timestamp field, a lot easier to understand than ticks from Epic, and our tracing tags, and that's it. That is our telemetry event. And the great thing about this type here is that you can just emit this as JSON to our Kafka topic, and you don't even have to write F#. So this became really important for us because we do have a lot of people at Jet who don't write F#. So for example, maybe you want to script an Nginx server with Lua to do some of this tracing, add metadata and add headers on incoming requests. That might be something you want to do. Maybe you're the data science team and you want to consume these telemetry events and maybe publish some of your own. So now you have a type to operate over that's sort of schematized that you don't even have to use our F# library for. Maybe you're in our Batman, which is our web team, and they have Node servers on their API. So maybe they want to emit telemetry events using a Node middleware. So now we've decoupled tracing from our F# library. So if you wanted to write F# because you were a product team and you use F#, we provided you great libraries for that. If you didn't want to use that, you could just write to our Kafka topic. So that was a great way to get around that issue. And remember, this is kind of how this relates, just to cement this home. This tracing telemetry type is basically inside that start event. So that's kind of what that structure might look like if we're trying to answer, show me which merchant had a failure, right? A failure is represented as a complete without a start. So another problem we faced when we tried to solve, real business issues for developers was our querying was not performant enough. So we sort of partitioned by trace ID, which made a lot of sense. But when it came to querying for merchants, which might be across many traces, and again, we're subject to time drift here. So getting a good sense of when these events are coming in within a given window can be difficult. So we weren't really sure how to solve, these complex queries, right? Like joining by merchant ID. So what we ended up doing was we created semantics around starting and stopping a span, so decoupled those, right, from our start and complete. And then what we did was add an operation name. So we sent those events to Cosmos DB. So they're written as our, that's our source of truth. Our Xray service consumes from our Kafka topic and indexes these events as they come in Cosmos DB. Now, a great feature of Cosmos DB, which we love at Jet because we do event sourcing, is something called the change feed.
What the change feed is basically a log of all these incoming events. As these collections get updated, these individual events will get written to this change feed. So we consume from this change feed, and we create a snapshot of all of the topology. So we bucket these traces by these top level key value pairs, and we send them to Splunk. Now, Splunk is an awesome tool. And actually, when we were doing requirement gathering, people at Jet just said, hey, Gina, can you just build like Splunk for tracing? We were like, I don't think so. But what we ended up doing was just sending those snapshots to Splunk and allowing people to do their own windowing and alerting. We didn't have to reinvent the wheel and make our own DSL for graph querying. All we did was allow you to join on Trace ID, look for events that had a start but not a complete, and you could window on your own SLAs. Maybe you're very sensitive to losing an event, so you want to immediately get alerted. Maybe you don't care, you just want to know that it finished within a day. We have some ETL jobs at Jet where maybe a day is okay. So we allowed you to set your own alerts and definitions, and we didn't try to solve everybody's problem. We just allowed you to configure it the way you wanted to. Another thing that we're kind of pursuing is there's a couple ways that you could go about validating that something is complete and an action is successful. Some companies approach this problem by creating a graph manifest file where you write ahead of time a definition for a graph. You say, okay, in my merchant SKU update flow, this is what it means to complete. It means these hops are seen within this SLA under this time frame or something. And the problem with that is, we could have done that. And then when you have events coming through, we kind of use this definition to sort of retrofit these events to that shape and say, okay, well, if it doesn't conform to this shape, then this DAG is not valid. The problem with that is some business user or developer has to maintain this graph file, and this graph file may not actually represent reality. You may scale up in certain places, you may change your system, and then you have to change this other dependency of a graph file. So that's not good. People don't want overhead. So what we're kind of pursuing is how could we add graph definitions via reflection. So let's say we utilize a feature of F#, we add attributes to the AST, and so when you compile your code, it has those operation names in there. So what we can do is add a script, and actually another team at Jet even wrote this script tool that parses your compiled code, generates information based on the attributes in that code, and then what we can do is retroactively have a graph definition from that code. So this is something we're still pursuing, but I think it's something that I would love to see more in industry, is kind of like auto magical graph definitions via reflection. I think that's closer to what people want than specifying a graph file ahead of time or somehow determining some anomalous pattern based on a z-score or some sort of histogram. So I don't think you can really set SLAs with a z-score or any sort of anomaly detection, and I do think the overhead of maintaining a graph file is not great. So reflection, definitely an avenue we're looking to pursue. And just to give you a high-level overview of our Xray architecture here, you see that microservice, that little mu symbol there, is emitting to a log, right? Remember I said it's logging asynchronously. And this file beat daemon, which is our message bus daemon, reads that log, forwards that to our Kafka topic. Our Xray service consumes from that topic, indexes in Cosmos DB, right? And then we have an Xray API, which basically we allow you to directly query Cosmos DB. Maybe you want to look for a trace, posthumously. You have, something went wrong. It was this trace that it started to go wrong at. You can look up a call graph based on that trace. And then we also have a new area of our Xray UI. Now, this UI has been super problematic, and I'll get to that in a moment. So the problem with our UI was most UIs that come with distributed tracing are kind of time series graphs of spans, which again, in an asynchronous system is not very useful. You want to know if this topology is good or bad. Did this action complete or not? So an SLA on that it's not a good fit.
So we allow teams to make their own dashboards in Splunk, and we're also we've iterated a few times on our current UI, but we're sort of playing with these force-directed graph views and hierarchical tree views. And another call out to open source is kind of hierarchical tree view dipping across many trees. There's not many UIs that do this well. I mean, some spring to mind, something like the cross-branch diffing that some of the JetBrains IDEs do might be one place my mind goes. But for something like a merchant, show me all actions which failed for a given merchant, that essentially means you're comparing maybe thousands of traces, potentially millions of traces, and you need to see which ones were anomalous. So what UI fits that best? That's an open area of research for us. So where are we headed in the future with Jet? We're headed more in a direction of unified logging. And what does that mean? Basically, managing a different logger for tracing versus, the metrics that you want to send versus, logging large exception strings. Those are all different loggers right now, and people might be instantiating loggers all over the place in their microservices. So what we want to get to is a pattern kind of more like what I showed you with async omega, where you can log to one logger in an ambient context, and depending on the type of thing you send it and how you've configured it, it might send to multiple backends. So it might send your tracing data to Splunk and Cosmos DB. It might send your metrics to our Prometheus DB or to New Relic, or your info events. They might go straight to your special Splunk index that you've set up, right? So we have a few different backends that we want to support. We want to support one logger with low overhead. That's kind of where we're headed. And that way, these events, these disparate event types can be actually aware of each other. So another thing there is schematization. Remember I said essentially a topology of a trace is services communicating, right, over different channels, and those channels are essentially schemas. So at Jet, if you want to share schemas, the only real way of doing that is to have different schemas or different DLLs that you share between services, and that's not good for transitive dependency purposes and other reasons. But neither here nor there. Schemas, a new place that Jet wants to get to, really important priority for us. Higher level abstractions, even the code I showed you is still too low level. So we really want to get to a way where it's simply auto magical, where you get great functionality out of box. So more integrations, more backends, more projections. That's where we're headed. And open source, question mark. I gave this talk also at SRECon, and someone came up to me and was like, Gina, why do you hate open source? Why don't you give back to OpenZipkin? And why do you need to reinvent the wheel at Jet? And I think his point was pretty valid, right? Like, why do we need to reinvent the wheel? I think partly because there wasn't a good fit for us, and we needed to make our own mistakes before we just kind of dump what we have in open source. So, we're still iterating internally, and I think the future of this is absolutely open source. So hopefully we'll see it there, and hopefully we can influence more of these types of open standards, especially to fit our use cases. All right, so
thank you.
This is kind of the lessons, some other stuff. Here's some important, fun things to read. Especially, I want to shout out, the blog post by Leo down at the bottom if you want to learn more about how Jet does event sourcing, stuff like that. And thank you guys so much for your time. This has been great.
Thank you for joining us. I think I had a look at the questions to see if people are asking something, but there was only one comment, which was saying, no questions, just applause and sympathy. A lot of what you're saying rings true to me. So I think looks like there's a lot of interest in the topic. So we don't have too much time for questions. So should we just wrap up, and I'll get Vincent on. It's a shame we couldn't do the call with you in the Jet offices, because then we could sort of we could figure out if Skype can actually transfer the smell of nice coffee.
We have so much nice coffee at Jet. And if you're curious about what the Jet offices look like, I really implore you to Google it, because we have a beautiful office. Today I had a cat emergency, so I had to take my cat to the vet. So that's why I'm calling from home. But thank you so much for having me. This has been really great.
Thank you. It's been a great talk and great pleasure to have you on FSurfConf. Thank you. And if you're watching us, stay tuned. We will have another talk from Vincent from Genetech starting in just a second.